Hi class, we are now on the chemical equations. So I briefly discussed reactants and products, but we're going to actually start putting these compounds into this general formula of a reactants on one side, products on the other, to determine chemical reactions and what's exactly happened. So here we have an equation, and what this is that we have carbon as a solid plus oxygen as a gas. And means a combustion or heat reaction produces carbon dioxide gas. So we have reactants on one side, we have an arrow, and the end of the arrow you have the reactants on the left side, and on the right side we have the products, and the tip of the arrow faces them. So this is a pretty easy chemical equation to look at. This is what we will use, and from this point on we're going to always use chemical reactions. So again, reactant side, reactants is just a fancy word for starting materials, starting chemical compounds of whatever we are trying to produce. And products means exactly what it is, what we have produced on the other side of the arrow. And that arrow means yields, produces, reacts. There's general words that you can use for this. We always, well, from the beginning maybe not, but we tend to use physical states. And as we go on in chemistry, you will always use them, because what you're going to find is that atoms, elements, compounds, they're not always in one general state. They come in different states, solid, liquid, or gas. And as this gets more complicated, we will start doing calculations, and we have values that are associated with a substance that's as a solid, a substance that's as a liquid, and a substance that's as a gas. So we need to know what those are. And generally, when you're looking at these reactions, the physical states will also indicate whether a chemical reaction has occurred or not. Okay, so let's go through. Now this is from another book, another class I teach. You have a table 7.1, but it's not as, did not go over all of these this way, so I took this from another book. A plus sign, that means it separates whatever the compounds that you are either on the product side or the reactant. It's simply stating that you have more than one reactant or you have more than one product, and you're separating them. You do not combine them all. So in this case we have carbon that's a solid, and it's going to react with oxygen that's a gas. But at this point when we're looking at it, it has not, so that's why we don't have them together. It's just a way of separating the compounds. The arrow, which we'll use, means that it reacts to form products. The S in a parentheses means solid, the L in parentheses means liquid, and the G in parentheses means gas, and the AQ means aqueous solution. This is a substance that is in water solution, aqueous. Again, we have HCl gas, and we have HCl that is an acid when it's an aqueous. So all these physical states are very important. And when you have a triangle on top, you may not always have a triangle on top though. Some things include it, some do not. Means reactants that are heated. So you can still be looking at a reactant that has heat, but you don't see the triangle on top. Okay, so symbols to write an equation. An arrow separates the reactants from the products. Reactants are written on the left side of the arrow. Products are written on the right with the tip facing those substances. Multiple reactants or products are separated by a plus sign, kind of like a comma. The delta sign indicates heat is used, but again, we could be dealing with a lot of reactants that actually heat is generated or used, and we don't have the triangle there. But in some cases you'll see it. Some books do, some books don't. Physical states, okay, so then we have two reactants on this side. We have, this is heat for this reaction, and product. So we have two products and two reactants on this. Physical states, again, so here we have the equation that I took from the first page. That's why it's blurry. And it shows carbon as a solid in the presence of oxygen as a gas. Heat is used here in this reaction, and it produces carbon dioxide gas. The reaction occurring in a natural gas flame is methane, and it reacts with oxygen to form carbon dioxide and water. So we can represent this reaction as such, where we have methane plus oxygen. It produces carbon dioxide and products. We're missing the physical states. We need the physical states because, as you can see here, water is not liquid, it is a gas. It's the steam, and you don't always see this. This is a combustion reaction, and steam is all being let off. Even if your eye cannot detect it, there is water there, and it's as a gas. Same as CO2. We don't see CO2 when we burn methane gas and oxygen, but the CO2 is there. We need to show it, and we need to let people know that this is a gas that we're dealing with. The chemical equation. So let's look at the combustion of methane. We're going to break this down. How many oxygen atoms are on each side? So we have here, this is the equation. This 2 here means that we have 2 oxygen atoms. Over here on this side, we don't have any with the methane. We have with carbon dioxide, we have 2. So you see the red here, this means the 2. Carbon is black. We have 2. But we have another product on this side, and we have water. And water has 1. We have 2 hydrogens, but we have 1. So on this side we have 3 oxygen atoms, and this side we have 2 oxygen atoms. So as you can see here though, that the reactants that you start out with, the starting materials, are still on the product side. They have just switched dancing partners. So we cannot create something out of nothing. That does not exist. We have to use what we're given, and it will switch partners if a chemical reaction has occurred. So what will happen is that the bonds that are attaching the hydrogens to this carbon will break, and as you see, it has a new dancing partner of oxygen. Same thing here. This oxygen is going to break apart, and it's going to split into some going to the carbon dioxide and some going to the water. All right, so let's take a look at the H atoms. We have 4 on the reactant side, and we have 2 on the product side. This is not a balanced reaction. This is just an equation. We always use balanced equations. In fact, if you don't, everything that you answer on an exam or quiz will be wrong, because we always go by a balanced equation. So I'm going to show you how to balance an equation. We cannot have odd numbers. They have to be even, not necessarily even, but they have to equal each other on this side. So if we have 4 atoms on this side, we need to have 4 atoms on this side. If we have 2 atoms on this side and we have 3, we need to find a number that allows a multiple to have the same number of atoms on both sides. That's what we're going to do. So this is where the coefficients come in. Now what this is that we can add numbers until we get the same number of atoms, and everything has to balance. So here a coefficient of 2 is added and a coefficient of 2 is added, but there's nothing here and there's nothing here. What that means is that this isn't implied that this is a 1 and this is a 1. If you have trouble balancing these in the beginning, write a 1 out. Write it out so that you can see. But in chemistry, we don't use a 1 when there's only 1 in substance. We just leave it as a blank, and it's that secret code or language that you're just supposed to know that there's a 1 there. So let's take a look at this. So we have methane, and the methane gas in the presence of oxygen gas produces carbon dioxide gas and water vapor. What this means is that we have 1 carbon. I have 1 here. Now how I do this, and no, everybody can do it their own way, but I keep a tally and I break all of them up and I do them in the way that they are presented, because some of these reactions get really big and there's a lot of reactants or there's a lot of products. So I keep them symmetrical so my eyes can see whether these are balanced or not. I don't switch these out. They are paired up, and I do them in the order they come. So carbon's first, so I have a carbon. I have hydrogen and I have oxygen. So let's look at this. I would write this out. I have 1 carbon, and I would write carbon. I would look, and I have 1 carbon. I go to hydrogen. I have 4. This subscript here, now let me explain what the subscript is. The subscript is attached to this compound. We never, ever, ever touch subscripts. If you have to adjust a balanced equation, you use a coefficient in the front only. If you touch these subscripts and change them, you are no longer dealing with the molecule that you have. You have something entirely different. So for instance, if I decide to add a 2 here, I no longer have water, I have hydrogen peroxide. So we never ever, repeat after me, never ever touch subscripts. We only add coefficients in the front. Okay, because then, as you can see, these molecules would not stay these molecules. All right, so hydrogen, we have 4, and I would see over here. So now sometimes you will have your atom split like the oxygen, so we'll take care of that one last. Over here I have hydrogen, I have 2, but I added a coefficient of 2, I have 4 here. So my carbon and my hydrogens are balanced. So let's take a look at oxygen. Oxygen here, I have 2, but a coefficient in front. You multiply these. So whatever's multiplied here, you multiply. So I'm going to multiply, let's handle this one first. So I'm going to multiply this with this. I'm going to have 4 oxygen. Now I have 2 atoms here. I'm going to multiply both. So that's where the 4 came in. So 2 times 2 for hydrogen is 4. and 2 times 1 is 2. So, is that right? Oh, I did an accident. What did I do? Oh, look at, I meant to do that. I have 2 oxygen here, but I also have 2 oxygen here. So 2 plus 2 equals the 4 oxygen. I messed up for a minute. Everything balances out. Even if that atom is spaced out between different compounds, everything will balance. Everything on this side should balance everything on this side, and we never, ever, ever touch subscripts, only coefficients. Okay, so let's look at this one. This is hydrogen gas plus oxygen gas produces water, and it's water as a liquid. So again, no atoms in a balanced equation, no atoms are lost or gained. We do not create something out of nothing. The number of the atoms in the reactant side is equal to the number of the atoms on the product side. That's where you see this equal sign. And we never ever touch subscripts. If we have to do anything, we add coefficients and we keep adding them until we get something that is balanced. And these are always whole numbers. In some cases, things get a little tricky, but we have whole numbers, no fractions. If we have fractions, then we have to get rid of them. So in this case, we have 4 hydrogens. That's with the 2 and the 2, which means that we have 4 hydrogens on the other side. We have 2 oxygen, and we have 2 oxygen. So this is a balanced equation. To expand it out a little more of what I'm looking at, this is, I just write 1C, but what it means is that there's a 1 times a C here. We have 4 times 1, because the 1 is here, of hydrogen, and we have 2 times O2, which is 4 atoms. So again, on this side, we have 1 carbon. We have 4 hydrogen atoms. We have 2 as a subscript, which we'd never touch, but we add a 2 here. That gives us 4. And we have 4 O atoms on this side. We need to have 4 on this side. So between these two, we have to have 4. So here we have 2, and here we multiply this as well. That's 2. So we have 4 O atoms on this side. And that gives us our total of 4. So we balance this out. Now let's do a problem. Write an equation using the correct formulas for the reactants and problems. So we have a formation of aluminum sulfide. We are showing that we have aluminum solid here and sulfur solid here, but through a chemical reaction, we produce another solid of aluminum sulfide, but this is not balanced. So we need to balance it. So first thing, write an inventory. I would write 1 aluminum atom. I would write 1 sulfur atom. I have 2 aluminum atoms, and I have 3 sulfur atoms, and this is not balanced. They have to equal on both sides. So this is where you start adding coefficients in. So because I have 2 aluminum atoms on this side, I would add a 2 as the coefficient on this side, and then I would come down and fix my table. Now once I fix one, I make sure that it matches whatever the other one is. I don't usually let go of that atom I'm working on until I get it balanced, and then I go on to the next one. So in this case, we have 3, so I add 3 here. So I have 3 sulfur atoms, 3 sulfur atoms. This is now balanced. So the coefficients have been added, and they are in their lowest ratio. That means that if we had numbers that we could divide and lower and reduce them down, we should. But if we can't, unless every compound, regardless of where it's at, can be reduced down. This cannot be, because if I divide anything, I'm going to start getting fractions, and we do not work with fractions. Okay, so in photosynthesis, plants make the sugar glucose from carbon dioxide and water. This equation is, and we have an x, so let's solve for the x. So we have our answer for this x is either going to be 3, 6, 9, or 12. So I pretty much wrote it out here. So we do our tally. So I have 6 carbons. I have 6 carbons. I have 12 hydrogens. And yes, I kind of went in a different order here, but that's because we've got to solve for oxygen. So that's why I jumped over to hydrogen. So we have 12 hydrogens. How do we have 12 hydrogens? Because 6 times 2 is 12 hydrogen atoms here. And now on this side we have 12. So we had 6 carbons. We have 12 oxygens, but we're not done because we have another one over here. And we have 6 oxygens. So we have 18 oxygens on the reactant side. On the product side, we have 12. We don't have to worry. This would be a 1 here. So it'd be 1 times 6, 1 times 12, 1 times 6. So we have 12 hydrogen atoms. We have 6 hydrogen atoms here, but we need to solve We have 18 on this side. We need to have 18 in total on this side. So this is where algebra comes in. We solve for x. So we have 2x equals, and the 2 is from the subscript. So if you're wondering where that comes from, because we're using a multiple of 2, it's not by itself. So 2x equals 18 times 6. 18 is the total that's on this side. 6 is the total that's on this side. And we subtract. We end up with 12. Divide everything by 2, and we have 6. So this answer would be, we would have 6 as a coefficient on this side of the balanced reaction, and the reaction would be balanced once we plug that 6 in. All right, so let's look at another one. Balance the chemical equation when solid, an iron oxide reacts with hydrogen gas to produce solid iron and water. Now, you're not at this level yet, but this is why you're learning how to to know chemical compounds, because eventually you will be given a sentence and you will have to complete it into a balanced equation with the physical states. So in this case, I've highlighted, it actually tells you what the physical states are. So when we get to this point, you should be able to write this out. So balance the chemical equation, we have Fe3O4, and it's a solid. We have a plus sign because we have something else on the reactant side, which is hydrogen gas, and hydrogen is a diatomic, meaning it's only found in its natural state in 2 IH atoms combined together, and it's a gas. We do an arrow, and it's saying that we produce solid iron, so it's just Fe with the S, plus water. And water, and when it's not stating what state it is, it's liquid. We just put it as an L. It's a pure liquid water. But this is not balanced. We have just simply wrote out an equation. We have to balance this out. So I do my tally, I set it up, I have my iron, my oxygen, and my hydrogen, and I do the same. So my eyes can easily tell if something's not matching. And we plug it in. So I have 3, I have 4, I have 2, I have 1, I have, oh, no, there we go, 1, and we have 2. Okay, this is simply what the same box is telling you down below. I need to fix this. So how am I going to fix this? Well, here's something, tips that I do. I handle the oxygen and hydrogens. There's a lot of them. And in most reactions, you're always going to have a hydrogen or oxygen. So I tend to do those last because of the fact that there tends to be more of them. I always want to tackle the atom that is the least, and it tends to be a metal. Also, this lone right here, this hydrogen gas, this is why I'm not going to touch hydrogen till the end, because once I balance everything, usually this lone guy here, whatever number I add in is how I tie everything together. And it's the same for an oxygen gas. If oxygen's by itself, I tackle everything else and leave oxygen for the end, because it's usually this final number is how I'm going to make everything equal. That's just me. Okay, so I'm going to tackle, and I've highlighted my steps. So I have a 3, but I have a 3. Oh wait, I have a 3 here, sorry. So I'm going to add a 3 here. So I add a 3. So now I have a 3 and a 3, and they're equal. Now, the problem is they may not stay equal. As these reactions get more complicated, you might have to jump back and forth from an atom to an atom, back to another atom that you've originally balanced. It's a lot of fun. Okay, so the next thing I'm going to do is I'm going to tackle oxygen. So here we have, the next one was we have 4 oxygen, but we have 1 oxygen here. So I'm going to add a 4. I'm going to make sure I have 4. So I have 3 and 3, and I have 4 and 4. However, it's now affecting the hydrogen. I've got to fix that. So I've got to correct what was there previous, which was 2. So now I'm going to correct that number as well and make it an 8. So now I have these 2 atoms balanced on both sides, but I don't have the hydrogen. So this is the one I'm talking about that is tied by itself. By itself, it is easier to balance because it is by itself and is the hydrogen. So hydrogen or gas or oxygen are usually the ones by themselves. I would always suggest to leave those till the end. Those are the ones that are going to tie everything together, just like now. I have everything else balanced. So I have 2, but I have 8. So what would be the number that would get me to 8? And that's the 4. That's what I mean by that's the last compound that's going to tie everything together. Now, Sometimes you might have to go back and correct other ones. When you do, you simply do what I did. With this one, affected this one and it affected this one. I changed the numbers simultaneously so I don't mess myself up. And if I look, this is now a balanced reaction. And that's it.